Hello and welcome to iitiansgateclasses once again. So today we are covering some more problems, which is traveling salesperson problem, TSP. This is also called TSP, traveling salesperson. So here we are given few nodes like 1, 2. You can consider these nodes as cities. Okay. And this is a complete bidirected graph. It means that there is a path from 1 to 2, as well as there is a path from 2 to 1. Okay, there is a path from 2 to 4, as well as there is a path from 4 to 2. Okay, similarly, we have roads within every city or every node, you can say. Within every set of city, every pair of city, we have a path. There is no missing path. Okay, and it is given that the weight of each path. Okay, once you go from 1 to 2, what is the weight? What is the cost of traveling 1 to 2? Okay, and what is the cost of traveling 2 to 1? So we can indicate that in form of 1, 2, 3, 4, a matrix also, right? Because this is a complete graph, complete bidirected graph. We can represent it. Okay, so from 1 to 1 it's 0. We are saying from 1 to 1 it's 0. Let me use some other color. From 1 to 1 it's 0. From 1 to 2, we are saying it will take 10 rupees or $10, whatever currency you can consider. So these are the costs. I'm just writing randomly. Okay, 80, 90, anything like 70, 40, 0, 60, 6, 11, 21, 0. Now this is given to you, and you have to start from one node and cover all other nodes exactly once and come back to that starting node. Suppose you are starting from here, 1, you will travel like in any order, any optimal order you have to find out in which you are going to travel. And you are going to visit all the cities exactly once. You will start with 1, you'll go to 3, 2, 4, and you'll come back to 1. Okay, so this kind of traversing is also called Hamiltonian. Okay. Hamiltonian graph. Okay. And it is not that this is NP complete actually. I will tell you what is NP, NP complete, NP hard, and P. But before going into it, let's see that what is the problem. You have to start from 1 and you have to traverse all other cities or nodes exactly once. You can't go back there again. Okay, and you have to find out the minimum cost, and you have to come back to this node also. So let me write this. Start from one node. Okay, start from one node, cover all other nodes exactly once, and come back. These all 3 conditions should be satisfied, and come back to starting node with minimum cost. Okay, this is your problem and you have to solve it. Now let's consider the algorithm of it. Suppose we are considering this graph only with these costs. Okay, and we are saying that okay, this problem is TSP. So we are starting from 1, and it is given that we are going to solve it like TSP 1, we are starting from 1 and we have to cover 2, 3, and 4 in any order. Okay, this is the set that we have given. So what is the solution? Solution is it's TSP 1, 2, 3, 4. Now after 1 you can either go to 2, 3, or 4, but you can't look just the immediate cost. You have to look in the future, kind of in future. You have choice. If you go to 2, and after 2, if you go to 4, the cost may be minimum. but from 4 to 3, the cost may be very huge. Okay, it may be very huge. So your choice is, if you go to 1 to 3 and you go to 4, that may be minimum. You don't know. Okay, you don't know. That is the problem you have to solve. So the solution for this one, as per the algorithm, is minimum of cost of 1 to 2 plus, again we apply same algorithm and we eliminate 1 for now. We will say that, okay, it is from 2 to 3, 4. Okay, either this or cost, you will go from 1 to 2 first. Then you say that, okay, let's see which one is the better one. I will go to 1 to 3. I won't go to 2. Then my remaining nodes are from 3 to 2, 4. Okay, or this one, either this one, or I'll go to 4, because it is a complete bidirectional graph, right? So I can go from any node to any node, or any city to any city. So it's TSP 4, 2, 3. Okay. So I have these 3 choices. Unless I solve all 3, I will never know that. Unless I will solve all these 3 problems, right? I don't know which one is better one. So I have to solve this one also. So we are generating kind of tree-like structure here, or it is a graph, because from last node you have to come back to 1 also. Okay, if you remember these steps, come back to the starting node with minimum cost. So from the last node, whichever it is, here the last node may be 3 or 4, here it may be 2 or 4, here it may be 2 or 3, but you have to go back to the 1. So let's consider this one. TSP. What if we solve this one? 2, 3, 4. Here we have 2 choices. Okay, minimum of either go to 2 to 3 first or 2 to 4 first. We will go from 2 to 3 and say that, okay, TSP of 3, 4. Okay, either this is the option or this is the option. 2 to 4 I will go, and I will go like TSP. I have already visited 4 from 2, then I will go from 4 to 3, then from 3 to 1. Okay, so to solve this one, you have to consider these 3 choices, and you will consider minimum out of these 3. You don't know minimum because you again have a sub problem here, and you have to solve this sub problem. Similarly, similar to this one, you will generate for this. Similar to this one, you will generate again for this one also and this one also, and it will keep on going until you have reached to the last node, and from that node you will go to 1 again. Okay, so let's see, what if we solve this one, TSP 3, 4. What is the TSP 3, 4 meaning? 3, 4. It means that it is equal to cost of 3 to 4, traveling from 3 to 4, plus TSP of 4 to 5. 4 to 5 means 4 to 1. 4 to 1. Okay, 4 to 1. And TSP of 4. Okay. TSP of 4, 5 means cost of traveling 4 to 1. Okay, so if you consider, if you go like this, if you choose this choice here, first one, and choose this choice here, suppose this is the minimum out of all these 3, this is the minimum out of these 2, and then there's no minimum. Okay, then if you add the cost, it is cost from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay, so it's basically, if you know that already, that these are the minimum. Okay, I'm just assuming that these are the minimum, the red arrows are the minimum. Then my total cost is, the minimum cost is 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay, this is my minimum path. I'm assuming it. But before considering the minimum path, you have to solve all these things. Okay, so let's try to write down this thing in generic way. Okay, so we have given a problem TSP. We have a starting point S, and we have a subset. subset like A, subset. Apart from S, we have A. Okay, so this is the subset of all the nodes except S. Okay, here you see that the subset is 2, 3, 4. Okay, so this is subset. A is subset of all nodes, and it have all nodes except S, the starting point. Okay, so what is the minimum one? It is, you will go from S to some node, like you can say some node A. Okay, S to A, right? You will go from S to A. Okay, and then you can say that, okay, the minimum of these things. Okay, not this one, sorry. It is the minimum of these choices. I'll go from S to some node K, where K belongs to this subset A. This subset A, okay? K belongs to this subset A plus TSP of K comma R minus K. Okay. So this is the generic. This is generic way in which I am writing. Okay. I choose K for all K. I choose K out of all the subset, or out of all the elements in the subset, whichever gives me minimum. I don't know which will give me minimum, but right now I'm considering that K will give me the minimum. Then I will again apply TSP K R minus K. Okay, let's consider example. We have written like TSP 1, 2, 3, 4. Now I'm saying that, okay, this set is A, and I'm choosing K out of this thing, K. And I will choose the minimum one. I don't know, till now I don't know which will give me minimum, but I'm choosing the minimum, which will lead to the minimum optimal solution. So I will say that, okay, 1, K and plus TSP of K comma this not R, sorry, it's not R, actually it's A. Okay, it's A minus K. Now this K could be anything, either 2 or 3 or 4, whichever will lead to the minimum cost. Okay, so this is the TSP solution. Now the property, the very basic property of TSP is that there is no dynamic programming solution for the TSP. There's no dynamic programming solution for the TSP. Traveling salesperson. Okay, so because all the function calls in the TSP are unique. So even if you save all the function calls, it won't lead you anywhere. Okay, so the number of function calls in TSP initially, you see here that how many options do we have? For 4 nodes, you have 3 function calls. And for each of these three, you have 2 options. For this one, you have 2 options, right? I've written 2 options here. For this one, you have 2 options. For this one, you have 2 options. And again, for this one, you have only 1 option. For this one, you have only 1 option, right? If we have 5 nodes, so you will have 4 calls here, 3 calls, 3 calls, 3 calls here. Then again, you have 2 and 2 calls. So similarly, if we track down number of function calls, you have initially your n-1. If we have n nodes, n-1 calls, then for each n-1, you have n-2 calls. For each this n-2, you have n-3 until 1. So this is factorial n-1. Okay. And if you apply the effort to find out the minimum out of these n-1 choices, it is around n. So this is factorial n actually. And factorial n is considered as n raised to power n, order of n raised to power n. So basically TSP is giving you order of n raised to power n, and there is no dynamic programming for it. Okay, there is no dynamic solution. No dynamic solution. Why? All function calls are distinct That's why there's no dynamic programming solution to it. Okay. Now let's move on to the next very important research topic. They will ask you a little bit about it. You should know a little bit about it. Okay. That what is NP hard and what is NP complete. Right? What is NP hard and what is NP complete. And what is polynomial time algorithm? What is exponential time algorithm? Polynomial time algorithm. So here this 2 raised to power n can be written as n raised to power n. In general, I have written this. Subsets of problem I haven't solved for you. It's same to this 0-1 knapsack only. It's very similar to 0-1 knapsack. Okay, so I don't have to solve each and every problem for you. You can reduce this 0-1 knapsack to subsets of problem. It's very easy. It's again 2 raised to power n. Now I am saying that this is a dynamic programming solution, but apart from without using any memory, it's actually giving you this much time. Okay, 2 raised to power n only. And for matrix multiplication, you have seen that it's n cube, but you are considering n raised to power n without dynamic programming, I'm saying. Okay. Now, what are we seeing here? Polynomial. What is polynomial time algorithms, which can be solved in polynomial time, whether it's n raised to power 1, n raised to power 2, n raised to power 3, n raised to power 100, or n raised to power 1000. But it should be solved in polynomial time. Here, n should be there and a constant power should be there, or logarithmic you can add, because logarithmic is for large value of n, logarithmic is far less than n, so you can consider logarithmic also, like n cube log n or n square log n or n log n. Okay, so we have seen all such algorithms. We have seen many other algorithms also, but right now we have seen these algorithms. For linear search, it's order of n. For binary search, it's order of log n. For selection sort, bubble sort, insertion sort, it's order of n square. For merge sort, it's order of n log n. For quick sort, it's order of n square in minimum, in worst case, and in average case, it's order of n log n. Okay, n log n. Quick sort is also a very good sorting algorithm. Worst case scenario is rare, but it's order of n square. So all these are polynomial time algorithm. Okay, it's polynomial. Then we have exponential time algorithm, like 0-1 knapsack you have seen. It's 2 raised to power n. Okay, for TSP, it's n raised to power n. For matrix multiplication, n raised to power n. Subset sum, 2 raised to power n. So this is a very huge pain for algorithm guys, okay, for algorithm researchers, because their main task is to reduce this algorithm, this exponential time problem into a polynomial time, or try to find out a solution where this algorithm, this exponential time algorithm can be converted into polynomial time algorithm, or find out a polynomial time algorithm for exponential time algorithms. Okay, so we have seen some dynamic programming solutions for this one, but that takes too much of the space. Okay, so these are few points that you must know before going into NP hard and NP complete. That a polynomial time algorithm for very large value of n, is always far less than exponential. Okay, so see here, if we raise the value of n 1 to 2, for example 2 to 100, it will be 100 power 100. Here it will be 2 raised to power 100. Then if you increase 1000, this power will remain constant, 100 power 100, like 1000 power 100. But 2 raised to power 1000 is exponential. It graph goes like this. Okay, if you draw the exponential graph, it goes like this. In polynomial graph go like this, or you can say this, right? So this exponential is the problem. Once the input size increases, exponential explodes. Okay, so this is the first point. Polynomial time is always better. Now, suppose you solved a exponential time algorithm in a better manner, in a better way, very good way. You solved an exponential time algorithm. Then the researchers they won't sit on each and every exponential time algorithm. There are so many variations of subset sum problem for so many variation of 0-1 knapsack. There are so many variations of 0-1 knapsack. They are not going to solve every variation of 0-1 knapsack. And even they are not going to solve 0-1 knapsack and TSP separately, and then matrix and multiplication separately, and subset sum separately. So what the idea is, there must be some association. The researchers generally, they associate these exponential time algorithms to each other. Okay, they associate. What is the association? The association is, we are given a problem A. Okay, we are given a problem A, and we are given a problem B, C, D. All these are exponential algorithms. Okay, we know that there are some algorithms, exponential algorithms, A, B, C, D, E, F, G. There are so many exponential algorithms. And there is this subset sum. Generally, there is a SAT, satisfiability problem, SAT. Let me write inside of subset sum, let me write SAT, SAT. I will define SAT very soon. Then there is this SAT problem. So right now what's happening that each researcher is focusing on solving this SAT, satisfiability problem, and try to reduce its complexity from exponential to polynomial. They are trying to reduce its complexity. There are so many like approximation algorithms, some linear approximation. There are so many, like once you go into the course of these fundamentals or these research, these like very core computer science research, they are trying to reduce the time complexity of SAT algorithm from exponential to raised to power n to some like some polynomial time or nearby a polynomial time, even if they are sacrificing some of the accuracy. That's called you can say that's called approximation. But once they are done with SAT, satisfiability problem, they are not going to solve all these problems. Okay. Suppose in future, if they have some solution for SAT, which takes, for example, n raised to power 10. Suppose, okay, they have some solution. They will find out some solution. The researchers work on SAT problem. Then the responsibility of other people or research area people is that let's have some reduction of each problem. For example, 0-1 knapsack or TSP problem. Try to reduce this TSP into SAT problem in polynomial time. What I'm trying to say here is, they are not going to solve TSP separately. They will try to reduce the TSP problem into SAT problem, satisfiability problem, okay, in polynomial time. For example, if reduction will take n raised to power 5, the TSP reduction will take n raised to power 5. Then how much time will it take? It will take like n raised to power 5 plus n raised to power 10. Because if SAT will take n raised to power 10, then this will be the total time complexity. n raised to power 5 plus n raised to power 10. n raised to power 5 plus n raised to power 10. Okay. So now what I'm saying is, the researcher work shows some association among exponential problems, so that if one problem is solved, we can reduce every other problem to that solved problem into polynomial time. Okay. So what I'm trying to say, let me repeat it again. SAT is a very known problem, right? So every researcher generally do that. They pick an exponential problem. They reduce that problem into, for example, I pick TSP, traveling salesperson problem. Okay, and I will reduce with some polynomial time, and this power k is constant here. You can consider k equal to 2. Okay, for example, it's n square, right? And I will reduce into SAT. Now, if everyone focuses on SAT problem, try to solve the SAT problem in some time, then it will take, for example, n raised to power p time. P is also constant. Then solving TSP will take n raised to power k plus n raised to power p. Okay. So I will take n raised to power k time to reduce TSP into SAT, and the SAT is already solved with n raised to power p, right? It haven't happened yet. Okay, it's still pending. Like researchers are working on it, but the idea is that let's focus on a single problem, exponential problem. Try to solve this one, and every other exponential time problem will be reduced to this SAT problem. Okay, this is how they are doing it. Now, if we don't have polynomial deterministic algorithm for exponential problem, what is the other way? It is known that there is no polynomial deterministic. So what is the difference between determinism and non-determinism? I will give you an example. Each and every statement of the algorithm is deterministically known. We know that I will write a step, then I will write another step, then I will write another step, and each step time complexity is known. Time complexity is known. It's order of n or order of 1 or order of like n square. Each step time complexity or what it is doing, it is known. So this is called determinism. Non-deterministic means for few steps I know, and for another steps I don't know. So I just left it there with some generic statement, or you can say generic method, which some other person will solve, or I will solve in the future. So let's see an example here. For example, I'm searching an element k into an array A. Okay, I'm searching the element A into an array A. I will write the problem something like this: that I found the index I. Okay, by using some non-deterministic algorithm in order of 1, which I haven't done yet. Okay, I haven't invented, or nobody else have invented yet. So that function will be called found function. Somebody will come and solve this later on, or I will solve in the future. So I will left it this place with some generic statement that found function will be there. It will give me the index. I will check that index element with k. If it's a success, it means that I found the element in the array. If I haven't found it, I will say that failure. The element k is not in the array. The element k is not in the array. Okay. So this is what these two are saying. And this will take order of 1 time. This will take order of 1 time. So all over, I am taking order of 1 time, which is better than log n, because there is a very good algorithm, binary search in sorted array. Binary search in sorted array, which take order of log n. So I'm performing better than that. So using non-determinism, I solved the searching of the element in order of 1 instead of order of log n. Right? So a non-determinism sometimes it looks like imagination, but you are assuming few functions, not all the functions. You are assuming few parts. Okay, and using some non-deterministic steps or some non-deterministic choices, you will get this index I. Okay, so later on I will invent this, or I will find out this found function, and I will perform these deterministic operations. So these are deterministic and this is non-deterministic. All over this function is non-deterministic. So this is what non-deterministic is. And if you have studied TOC, theory of computation, you already know that what is non-deterministic. If we have many choices, we non-deterministically choose a better choice, always a like best choice, always choose a best choice. Like for example, in 0-1 knapsack, let me erase this thing. Okay, like in example 0-1 knapsack, you have an item I. Okay, item I. Now, whether to choose this item or not. For example, you know that in order of 1 or order of n, you know that whether to choose this item or not. In polynomial time, if you know that for a current item, the ith item, and ith item can go from 0 to n, and if you know that whether to choose this item in polynomial time, okay, then the whole 0-1 knapsack can be solved in polynomial time, okay, without using dynamic programming. So you define some non-deterministic step that let's find out like whether to choose this one or not, like 0-1 choice, and I pass the item I in the method, and it will give me either true or false, and which is correct. So using this non-deterministic step, you solve 0-1 knapsack in polynomial time. Okay. So this is what called non-deterministic polynomial algorithm, in which the algorithm is not deterministic, but it's non-deterministically polynomial. Okay. Now let's talk about the standard problem, which is SAT problem, satisfiability problem. Here we are given with some of the here we are given with a CNF, conjunctive normal form. Okay, this is conjunction. We are given with some variables like x1, x2, x3. So this is x1, disjunction x2, disjunction x3. x2 is not actually x2, it's x2 dash, negation of x2, and this is disjunction. So you can consider this is as OR operation and this is as AND operation. Okay. Then you are doing x1, x2, x3, x1 dash or x2 or x3 dash. Okay. Now you have to identify for which value of x1, x2, x3 this will be 1 or satisfied. Now, how many choices do you have actually? You have n choices, 2 raised to power n choices for n variables. For example, we have 3 variables, right? Okay. How many choices we have? 8 choices, right? You have 8 choices, 2 raised to power 3 choices. If you have 3 variables, you have 2 raised to power 3 choices, right? If you have n variables, you will have 2 raised to power n choices, right? Why? Because each variable takes 0 or 1, 0 or 1, 0 or 1. So you have 2 raised to power n choices. And for you will try 2 raised to power n times you will try to satisfy this CNF. So how much time will it take? 2 raised to power n time it will take. So this is satisfiability problem or SAT problem, right? Now, it is known that the SAT problem is NP hard and NP complete. NP complete means, sorry, the SAT problem is known to be NP hard as well as NP, non-deterministic polynomial. It is non-deterministic polynomial. It is also NP hard. It is also NP hard. SAT problem is also NP hard, and it is also can be solved non-deterministic polynomially. So there is a very huge theorem for that or proof for that, why the SAT problem is non-deterministic polynomial and why it is NP hard. Okay. So I'm not going to go in the proof because that is a separate research topic or research subject. And if there are some research students taking this course, please go ahead and choose some standard books and for drill down more into it. I'm not going to go deeper into that. Okay. So it is known that SAT is basically NP hard and NP. So whichever is NP hard as well as NP is called NP complete. Okay, is called NP complete. Now there is a transitivity rule. If any problem, there is a problem P1. There is a problem P1. If the SAT problem can be reduced into P1 polynomially, for example, n square, n cube, or n5, some power of n. Okay, some constant power of n. If I can reduce the SAT problem into P1 polynomially, right? Then this problem will also be NP hard. Okay. Now, if P1 is reduced to P2 polynomially, for example, it will take n raised to power k1, it will take n raised to power k2, right? SAT can be reduced into P1 with n raised to power k1. P1 can be reduced into P2 with n raised to power k2. So how much time will it take transitively? SAT, this is transitivity, right? A imply A is reduced to B and B reduced to C. So we can say that A is reduced to C somehow. If it will take n raised to power k1, n raised to power k2, this will take. So A can be reduced into C1 with transitivity n raised to power k1 plus n raised to power k2. Okay. So this is also polynomial, right? So this is how this SAT can be reduced into P1, P2, and P3. So all these will be NP hard. This is the rule that if a NP hard problem is reduced into a problem, given problem P, some P5, okay, then this will also be a NP hard problem, okay. Now look at this diagram. Let me draw this diagram again. We are saying that we have a set of problems which are basically what? NP hard problems. For example, we have SAT problem, we have some more problems, for example, 01 knapsack, okay, traveling salesman, salesperson problem. Now, we also have NP. NP means non-deterministically, SAT can be solved polynomially. And every polynomial problem is subset of NP, right? So this area, this common area is called NP complete, denoted as NPC. Okay. So if 01 knapsack, if SAT can be reduced into 01 knapsack, this is also NP hard. And if 01 knapsack can be solved non-deterministically polynomially, then this is also will lie here, 01 knapsack. Actually, 01 knapsack is NPC. Okay, so there is a list of problems, and you can check that list that which all problem are NPC actually. To prove that a problem is NPC, you need to prove two things. You need to reduce the SAT problem into that problem. For example, you want to prove that P1 is NPC. You need to reduce the SAT problem into P1 problem, and your first step is this one, okay? Second step is you need to prove that P1 is NP. Okay, so remember that if you want to prove that a problem P1 is NP, non-deterministically polynomial, NPC, non-deterministically polynomially complete, NP complete, okay? Then you need to reduce the SAT into P1, or what you can say that either you can do this, or you can reduce SAT into some other problem P2, and you can reduce P2 into P1. You can make a chain of it, okay? You can make chain also. Like you can reduce P2 to P3 and P3 to P1. P1. First is this step, P1. Second one is you need to prove that P1 is NP. Okay. So using these two proofs, you can say that P1 is NPC. Okay. So there is a whole lot theorem for that. So thank you all for joining. That's it for today. And I think that is the end of algo. If something is remaining, I will record one more lecture. Thank you all.